Good morning, students. In the last session, we have discussed about the second type of isomerism, that is stereoisomerism. In stereoisomerism, we have discussed about the geometrical isomerism and optical isomerism. In optical isomerism, again, we have studied about the three types of optical isomerism, that is enantiomerism, diastereomerism, or we can say enantiomers, diastereomers, and mesocompounds. In today's class, we will be discussing about the next concept of stereochemistry, that is, we will be discussing about the projection formulae. So, let us begin today's class. Before that, we'll see the some basic term, that is racemic mixture. We will be coming across a term, that is racemic mixture. Racemic mixture is nothing but it is an equal amount of two enantiomers that we call as a racemic mixture. That is equal amount of the two enantiomers is nothing but racemic mixture, and a racemic mixture is optically inactive. Optically inactive is nothing but that is it has no effect on the plane polarized light. That is, it doesn't rotate the plane polarized light either to the left side or to the right side. That we call as optically inactive. So a racemic mixture, if you take any racemic mixture, it will be optically inactive. Optically inactive in the sense it doesn't rotate the plane polarized light to either of the sides, either to the right or to the left side. So such type of compounds or molecules we call as optically inactive compounds or optically inactive substances. So example for this racemic mixture is, that is 50% of D-tartaric acid and 50% of L-tartaric acid mixture is example for the racemic mixture. Next we have is a projection formula. Formula used to represent the molecules having three-dimensional structures on a two-dimensional surface are called projection formula. That is, projection formulae are the formulae which we are using to represent three-dimensional molecules, or we can say three-dimensional structures on the two-dimensional surfaces. On the two-dimensional surfaces is nothing but on board, or we can say on the paper, or we can say on the blackboard. Those are the two-dimensional surfaces. So these formulae are used for representing the three-dimensional molecules or three-dimensional structures of the molecules on a two-dimensional surfaces such as paper, blackboard. So such type of formulae we are referring as a projection formulae. The projection formulae that are used to represent chiral or achiral molecules are, that is, here there are some of the formulas which we are using for representing both chiral as well as achiral molecules. So those projection formulae are, there are 5 projection formulas to represent the chiral or achiral molecules. Those are, first one is flying wedge projection formula. Second is Fisher projection formula. Third one is Sawhorse projection formula. Fourth, Newman projection formula. And the last one is Zigzag projection formula. So let us see how we represent the molecules, that is three-dimensional structures, using these projection formulae. So let us discuss how we can represent the molecule using these formulas. First one we have, that is flying wedge representation. First type of representation or first projection formula is flying wedge representation. This kind of representation we are using usually for the molecules which are containing chiral carbon atoms, or we can say chiral centers. What we are telling, this flying wedge representation or flying wedge projection formula we can use for the molecules or for the compounds which are containing chiral carbon atoms, in the sense which are containing the chiral centers. So such molecules, for representing such molecules we can use this flying wedge representation. Here in this representation or in this formula, we will be coming across three types of bonds. That is, we use three types of bonds in this representation. That is, first bond we can say is the ordinary line. See here, this is the molecule. I am taking it as an example. That is R-lactic acid. This is a R-lactic acid wherein the chiral carbon atom. This is a chiral carbon atom. Why? Because it is bonded to four different groups. COH, OH, H and CH3. It is bonded to four different groups. So this central carbon atom is a chiral carbon atom and this is called as a chiral center. Here in this representation we are observing three types of bonds. The first type of bond we can say is the ordinary lines. See here, carbon is bonded to COH by a straight line or a ordinary line and it is also bonded to CH3 group by a ordinary line. These ordinary lines are present or they are represented in the plane of the paper. These ordinary lines represents the bonds. These ordinary lines represents the bonds which are bonded to the chiral carbon atom in the plane of the paper. That is bonds in the plane of the paper. And the second type of bond we can see is a solid wedge. This solid triangle is called as a solid wedge. We are calling it as a solid wedge. This solid wedge, it represents bond above the plane of the paper. It represents the bond which is present above the plane of the paper. That is bond projecting towards the observer. We can say this bond is projecting towards the observer in the sense towards the viewer, towards us. It projects or it is pointing towards the observer or towards the viewer and it is present above the plane of the paper. That is solid wedge is nothing but it is a bond. It represents the bond which is present above the plane of the paper, or we can say it is a bond towards the viewer or towards the observer. And the last third type of bond is we call it as a hashed line or broken line. See here you can see the broken lines or you can tell it as a hashed line. This broken line indicates the bond which is below the plane of the paper. We say this as a bond below the plane of the paper, that is it is projecting away from the observer. This solid wedge is projecting towards the observer, whereas this broken line will be projecting away from the observer or away from the viewer, or we can say away from us. So such type of bond will be representing below the plane of the paper. So this is about the flying wedge representation. In flying wedge representation, what we have to keep it in mind is that it will be containing the chiral center. Means this type of representation we are using only for the compounds which are containing the chiral centers or chiral carbon atoms. And here in this representation, we will be observing three types of bonds. One is the ordinary lines which represent bond in the plane of the paper. Second type is a solid wedge. It represents bond above the plane of the paper. And third type of lines are broken lines which represents the bond below the plane of the paper. So this is a flying wedge representation. Second we have that is Fisher projection formula. Second type of formula is a Fisher projection formula. Here in this Fisher projection formula, we are using a cross line to represent the molecule. See here, I am taking the example of lactic acid. Here there is a chiral carbon atom at the center. It is bonded to four different groups, that is CH3, COH, OH, H. I am taking the example of lactic acid. How we can represent the three-dimensional molecule or three-dimensional chiral molecules in the two-dimensional formulas that we will see using the Fisher projection formula. So in the lactic acid we have a chiral carbon atom. So in the projection formula what we are doing is the first step we are doing or we are representing the chiral molecule. First step in the Fisher projection formula is to represent the chiral carbon atom or chiral center. Here in the Fisher projection formula, we are drawing a cross line. See here, plus. It is like a plus sign. We are using a cross line to represent the chiral molecule, or at the center of this cross section or intersection of these two cross lines indicates the chiral center or chiral carbon atom. That is, in this projection formula, we are using a cross. Cross is nothing but a positive like sign. We are using a cross to represent the chiral carbon atom, or we can say asymmetric carbon. Here at the center, that is at the center, or we can say point of intersection of the lines is nothing but the chiral carbon atom. At this center or at the point of intersection of both the lines, that is a horizontal line and a vertical line, indicates the point of intersection of these two lines indicates the chiral center or chiral carbon atom. And the four bonds, see here, carbon is bonded to four groups. There are four bonds to the carbon atom. So those four bonds are represented by vertical and horizontal lines. See here, this chiral carbon atom is vertically bonded to, it has two vertical bonds bonded to COH group and hydrogen atom. So at this point of intersection, we have chiral carbon atom. So we are drawing two, that is vertical lines to represent vertical bonds. These are the two vertical bonds. One is bonded to COH group. So draw one vertical line and represent COH group. And below we have another vertical line, that is vertical bond which is having hydrogen atom. So we are drawing another vertical line bonded to hydrogen atom. So, and the horizontal lines, horizontal bonds, we are representing by a horizontal lines bonded to two different groups, that is methyl group and hydroxyl group. So, there are four bonds which are bonded to the four different groups with the chiral carbon atom are represented by four bonds, that is two horizontal bonds and two vertical bonds. And that vertical lines, we can say here in the Fisher projections formula, we are referring them as a vertical lines. We are referring this as a vertical line and this as a horizontal line. So vertical line represents, or it is pointing away from the weaver. Vertical line is this, bonded to a COH group and hydrogen atom. It represents the projection away from the observer, or we can say it is pointing away from the observer, whereas this horizontal line is pointing towards the observer. Horizontal line is pointing towards the observer, whereas the vertical line is pointing away from the observer. See here, one more example I am taking to explain you how we can write the projection formula. See here, I am taking the example of 3,4 dibromohexane. This is a 3,4 dibromohexane. See here, we have CH3, CH2, CH, CH, CH2, CH3. That is third and fourth carbon bonded to bromine. So 3,4 dibromohexane. First step is to identify the chiral carbon atoms. What is the first step? We will be writing the cross line to represent the, that is chiral carbon atom. So whatever the given compound is, or whatever the given molecule is, first you have to identify the chiral carbon atom in the molecule. So here we have given that is 3,4 dibromohexane. So first step is to identify the chiral carbon atom in the molecule. So see here we have, that is first, if I start numbering from both the sides, I will be getting the same nomenclature. So we will be writing it as 3,4 dibromohexane. So refer the first carbon atom. We have to identify, or we have to detect or determine the chiral carbon atoms in the given molecule. So we will be starting from the first carbon atom. This is the first carbon atom. It is bonded to 3 hydrogen atoms and this whole as a fourth group. There are 3 hydrogen atoms, so 3 groups or atoms bonded to this, and another group, that is fourth group, bonded to this first carbon atom. Means this carbon atom is bonded to 3 similar hydrogen atoms. It is bonded to 3 similar atoms, that is hydrogen atoms. So this will not be a chiral carbon atom. So this is not a chiral carbon atom. First carbon atom is not a chiral carbon atom. So move on to the next carbon atom, that is second carbon atom. Again this second carbon atom is bonded to this CH3 group. then again bonded to two hydrogen atoms, then another bond is to the this whole group as a fourth group. So this second carbon atom is bonded to CH3 group, then hydrogen, hydrogen, and this whole group. So again this second carbon atom is bonded to two similar atoms, that is two similar hydrogen atoms. So this cannot be a chiral carbon atom. So this is not a chiral carbon atom. So next we'll move to the third carbon atom. See here in the third carbon atom, it is bonded to a hydrogen atom. Then this whole group, that is second group as this one. Then third as a ethyl, that is CH2C, C2H5. Then another it is bonded to bromine. So this carbon atom is bonded to four different groups, that is Br, C2H5, H, and this whole group. So this will be a chiral carbon atom, that is third carbon atom will be a chiral carbon atom. Why? Because it is bonded to four different groups. So third carbon atom is a chiral carbon atom. So moving to the next, see here the same exactly the second, that is fourth carbon atom is also bonded to a hydrogen atom, then this whole as one group, bromine as one group, then ethyl as another group. So again it is also bonded to four different groups, so which means that this is also chiral carbon atom. So this third and fourth carbon atoms are chiral carbon atoms. So means in this molecule we have two chiral carbon atoms. If we move to the that is fifth carbon atom, again it is bonded to two similar hydrogen atoms. So it could not be a chiral carbon atom. So again to the sixth carbon atom is also bonded to three hydrogen atoms. So it will not be a chiral carbon atom. So in this whole molecule we have, or we got to know that there are two chiral carbon atoms present in the molecule. Those are 3 and 4, that is third and fourth carbon atoms. Third and fourth carbon atoms are the two chiral carbon atoms present in the molecule. So now we have completed the first step, that is to identify the chiral carbon atoms. Now we came to know that there are two chiral carbon atoms in the molecule. So next step what we have to do is we have to represent the chiral carbon atom, these two chiral carbon atoms, by a cross lines. See here we have two chiral carbon atoms, so we are drawing two lines. We are drawing two lines, means two chiral carbon atoms. We are drawing two cross sections, or two intersection points. At the first point we have, that is third chiral carbon atom, and at the second cross section or second intersection point we have fourth chiral carbon atom. So this one is the third chiral carbon atom and this one is a fourth chiral carbon atom. See here, third chiral carbon atom is bonded to, see this one, third chiral carbon atom is bonded to C2H5. That is, draw a vertical line and represent with the C2H5 group. And it is again bonded to Br. So it is bonded to Br. Again it is bonded to hydrogen. So we are writing as a hydrogen. Next, fourth chiral carbon atom. This is a fourth chiral carbon atom. It is bonded to hydrogen. So writing here hydrogen. Then it is bonded to bromine. So we are writing it to bromine. And again it is bonded to C2H5 group, that is ethyl group. So write the ethyl group. So here we have two chiral carbon atom. So we are drawing two point of intersection to represent two chiral carbon atoms, and then writing all the groups bonded to those two chiral carbon atoms. So this is about the Fisher projection formula. Here what we have to remember is that we have to first identify the chiral carbon atom present in the molecule. Then using the point of intersection for representing the chiral carbon atom, we have to draw the Fisher projection formula. So the next projection formula we have is that is Sawhorse projection formula. The third type of projection formula is Sawhorse projection formula. So this Sawhorse projection formula gives us a spatial relationship between the substituents or groups attached to two adjacent carbon atoms. Here the two carbon atoms can be either chiral carbon atoms or they can be a chiral carbon atoms. Means this Sawhorse projection formula we are using in the case of molecule or in the case of compound which is containing two carbon atoms. Those two carbon atoms can be chiral or they can be achiral carbon atoms. This gives us information regarding the spatial relationship or spatial arrangement of the atoms, that is between the substituents attached to the two adjacent carbon atom. It gives us the information regarding the spatial arrangement of the adjacent atoms, two carbon atoms, and the other groups bonded to those two chiral carbon atoms, or we can say two achiral carbon atoms. We are getting information regarding the uh, groups or substituents which are attached or bonded to the two adjacent chiral or achiral carbon atoms. See here in the diagram, you can understand this. See here, this one is a first chiral carbon atom and this one is a second chiral carbon atom. It can be a achiral carbon atom. So here Sawhorse projection formula gives us a relationship between the spatial arrangement of these groups which are bonded to two adjacent carbon atoms. These are the two adjacent carbon atoms. Here we are getting information regarding the groups. These are the groups bonded to the atoms, carbon atoms. So we are getting information, or it shows spatial relationship or arrangement of these groups for the two adjacent carbon atoms. Here in this representation, the bond between the two carbon atoms, that is bond between any two chiral carbon atoms or achiral carbon atoms, is represented by a diagonal line. We have to draw a diagonal line and we have to slightly elongate the line. We have to slightly elongate that line. First we have to draw a diagonal line between the two chiral or achiral carbon atoms. Then we have to slightly elongate that line and the remaining bonds are shown by small lines. These are the two carbon atoms. We are drawing a diagonal line and slightly elongating that line, and these points indicates the two chiral or chiral carbon atoms, and the small lines, we are drawing small lines to represent the groups bonded to the chiral or chiral carbon atoms. We are representing the other bonds to the carbon atoms by using small lines. This lower left hand, you have to imagine that the observer is this side. If the observer, you have to imagine that the observer or the viewer is weaving the molecule from this side. So the lower left hand, this lower left hand carbon is taken as a front carbon. This is a first carbon atom, this is a second carbon atom, this is fourth carbon atom, sorry, this is third carbon atom, and this is a fourth carbon atom. So this lower left hand carbon is taken as a front carbon, and this upper right hand, this one is a upper right carbon atom, this one is a left carbon atom, lower left carbon atom, this one is the upper right carbon atom, it is taken as a back carbon or rear carbon atom. This left hand carbon atom is taken as the front carbon atom. It is taken as a front carbon, whereas the upper right carbon is taken as a back carbon atom or rear carbon atom. Here in this Sawhorse projection formula, you will be observing two forms. One is the eclipsed form, another one is a staggered form. You will be observing two forms. One is eclipsed, another one is a staggered form. Here there is a free rotation about the carbon-carbon bond. This is a carbon-carbon bond. This bond, you can observe free rotation between these carbon-carbon bond, and also the three bonds attached to the carbon atom can be rotated in the clockwise or anti-clockwise direction. We can rotate these three bonds bonded to the carbon atom either in the clockwise direction or in the anti-clockwise direction with respect to the this center carbon atom. With respect to this carbon atom, we can rotate these three smaller bonds either to the right side or to the left side, or we can say either to the clockwise direction or to the anti-clockwise direction. Here what we are telling in the Sawhorse projection formula, we are using using this representation or formula to represent the atoms or to represent the molecules or compounds which are containing two chiral carbon atoms or achiral carbon atoms. Here the bond between the two chiral or achiral carbon atoms is represented by a diagonal line, and that diagonal line is slightly elongated, and at the ends it represents the carbon atoms, and the bonds which are attached or bonded to the other groups which are bonded to the carbon atoms are represented with the smaller lines. And this representation gives us information regarding these groups attached to the two carbon atoms, and the bonds which are or the groups which are bonded to these two carbon atoms, they can be freely rotated either in the clockwise direction or in the anti-clockwise direction. And here you will be observing two types of forms. One is eclipsed form, another one is a staggered form. And here you will be observing, or you may see that carbon may be viewed as a letter Y. See here, this carbon atom can be viewed as a letter Y. This is an inverted letter Y. Here also you can observe it as an inverted letter Y. But here in the staggered form, one carbon atom you can view as a letter Y. So next we have is the, that is next projection formula we have is that is Newman projection formula. Here in the, that is in the Sawhorse projection formula, the first conformation, that is eclipsed conformation, and the second conformation, or we can say second form, is the staggered form. In the second form, the groups on the second carbon atom and the third carbon atom, they are oriented away from each other. They are oriented away from each other. That is why we are referring this as a staggered form, means here the groups which are attached to the second carbon atom and third carbon atom, they are oriented away from each other. See here, this methyl group and methyl group are far away from each other. So this form is called as a staggered form. Whereas in the eclipsed form, the groups are oriented nearer to each other. This methyl group is nearer to methyl group, and hydrogen atoms are nearer to hydrogen atoms on the third carbon atom. Whereas in the staggered form, see here, that is at the second carbon atom, we have methyl group here. This methyl group and the methyl group on the third carbon atom, they are oriented far away from each other. Whereas the hydrogen atoms are also oriented far away from this third carbon atom, hydrogen atoms. The hydrogen atoms which are bonded to third carbon atom, whereas the hydrogen atoms which are bonded to the second carbon atom, they are oriented away from each other. So such type of conformation or such type of form of projection formula we are referring as a staggered form. Whereas the eclipsed form, in eclipsed form, you will be observing the groups attached to the carbon atoms, they are present nearer to each other. Means the groups which are attached, bonded to the second carbon atom, and the groups which are bonded to the third carbon atom, they are nearer to each other. That type of form, or that type of projection formula we are calling as eclipsed form. Next one we have is a Newman projection formula. The fourth type of projection formula is a Newman projection formula. This formula represents, again it also represents the spatial representation of, or spatial arrangement of all the groups that is present on the adjacent atoms. All the groups, that is spatial relationship between all the groups that are bonded to the two adjacent carbon atoms. Here the molecule is observed along the axis, that is carbon-carbon bond. Here also in the Sawhorse projection formula, we are observing the molecule along this axis, that is carbon-carbon bond. Similar in the similar way in the Newman projection also, we are observing the molecule along the axis, that is C single bond C, that is carbon-carbon bond. We are observing the molecule along the axis, that is carbon-carbon bond. Here this is the Newman projection formula. Using Sawhorse projection formula, we will be writing the Newman projection formula. You will be observing the molecule in the Newman projection along the axis, that is carbon-carbon bond. Here it will be a carbon-carbon bond. You have to imagine, that is you are observing the molecule from this side. You are observing the molecule from the front side. Here the carbon atom nearer to the observer is known as front carbon. See here, first you have to remember the front and back carbon atoms in the Sawhorse projection formula. This is a Sawhorse projection formula. In the Sawhorse projection formula, if we imagine the observer or if we imagine the viewer in this side, this will be the front carbon for the weaver, and this will be the back carbon for the weaver. So this will be the nearer carbon, we can say nearer carbon, and this will be the back carbon for the weaver. So this nearer carbon, or we can say the carbon atom nearer to the observer, is known as front carbon and is shown by a point. Here this nearer carbon atom which is nearer to the observer is shown by a point. It is shown by a point, and three groups or atoms which are attached to it are shown by three lines. They are shown by three lines here. See here, this is the nearer carbon atom to the weaver. So this nearer carbon atom is represented by a point, and the three bonds attached to this front carbon are represented by three lines. They are represented by three lines or three bonds. So the second that is first carbon atom is represented by a point, and it is bonded to three hydrogen atoms. Those three hydrogen atoms are bonded by three lines. So write the three hydrogen atoms. So this completes the representation of the first carbon. So next move to the third, that is a second carbon atom. And one more point you have to remember is that the three hydrogen atoms, or in general if we can say three groups or three atoms which are bonded to this carbon atom, they are shown by three lines which are at an angle of 120 degree each other. There is a 120 angle between the three hydrogen atoms, between, that is from this hydrogen to this hydrogen there is a 120 angle, from this to this 120 degrees, from this to this 120 degrees. So total it will be 360 degrees. So this front carbon is represented by point, and it is bonded to that is three different hydrogen, three different groups which are represented by lines. So here we have three hydrogen atoms. So represent those three hydrogen atoms, and they should be, that three lines should be at an angle of 120 degree each other. They should be at an angle of 120 degree each other. The next point we have to write is, that is the carbon away from the observer. Now we have represented the carbon which is nearer to the observer. Now move on to the carbon atom which is far away from the observer, or we can say which is away from the observer, or we can say back carbon atom, that is back of the observer. It is called as a back carbon atom. So this back carbon atom is represented by a circle. This circle is nothing but it is a back carbon atom. This point is nothing but a front carbon atom, and this back carbon atom is represented by a circle. It is called as a back carbon atom, and three groups bonded to this, or three atoms bonded to this back carbon atom, they are attached to it as shown in the figure. They are attached to the circle, or we can say they are bonded to the carbon atom as shown in the figure. That is, we are representing those bonds with the shorter length at the angle of 120 each other. These bonds are also at the angle of 120 each other. All the three bonds are at the angle of 120 degree each other. So this is the representation of the molecule in the form of Newman projection formula. Next, the last type of projection formula we have is zigzag projection formula. The last type of projection formula is zigzag projection formula. Here this zigzag projection formula, we are using it to represent the compounds which are containing two or more chiral centers. Here this projection formula we are using for the carbon atoms, or the molecules which are containing, or the compounds which are containing two or more chiral carbon atoms. Whereas for the earlier we are using the representation, or we are using the formulas for both chiral as well as achiral molecules, or for both the compounds containing achiral or chiral carbon atoms. But in the zigzag projection formula, we are using this projection formula or this representation for representing the compounds which are containing two or more chiral carbon atoms. And it is used for the chiral centers which are having hydrogen atoms as one of the substituents. See the example, that is I am taking the example of D-glucose. what we are telling, we are using this representation only for the compounds which are containing chiral centers with the hydrogen as one of the substituent. Means it should contain at least one hydrogen atom as the substituent. It should contain at least one hydrogen atom as one of the substituents. And this hydrogen atom is not drawn in the projection formula. We are not showing this hydrogen atom in the projection formula. See here the second carbon atom. We can say that here in the second carbon atom we are not representing the hydrogen atom. In the zigzag projection formula, what we are telling, it should contain at least hydrogen atom, at least one hydrogen atom as the substituent atom or substituent group. Means this projection formula should contain the hydrogen atom, one of the hydrogen atom as the substituent group, and that hydrogen atom we are not representing in the projection formula, or we are not drawing that in the projection formula. See here at the second carbon atom, fourth carbon atom, third carbon atom, we are not representing the hydrogen atom. So this, in this type of zigzag projection formula, will not be representing the substituent group, that is substituent hydrogen atom in the molecule. And this representation we are using for the compounds which are containing two or more chiral carbon atoms. So this was all about today's class. Here in this class we have discussed or we have studied about the projection formulae. That is, these are the formulas or representations which we are using for representing three-dimensional molecules or three-dimensional structures on two-dimensional surfaces. We can say that is on blackboard or on paper. So here we have discussed or we have studied about 5 types of the formulas, that is flying wedge projection formula, Fisher projection formula, Newman projection formula, Sawhorse projection formula, and zigzag projection formula. These are the 5 types of representation of the molecules. This you have to remember. In the next class, I will be discussing about the interconversion of these projection formulas. Means how we can write the one projection formula or representation in the one projection formula to another representation. For example, by taking the molecule or representing the molecule in the Sawhorse projection formula, interconverting that into Sawhorse projection formula, from Sawhorse to the interconversion to the Fisher projection formula. So in the next class, I will be discussing about the interconversion of the projection formula. Thank you.